Hello everyone. So in this video we are going to start a new topic, that is the Laplace transform. And we have already seen about Fourier analysis of a signal. So we have seen the Fourier analysis are extremely useful in studying of many problems of practical importance. So we have studied about signals and LTI system, and we calculated their Fourier series and Fourier transforms to get an in-depth about the signals and systems. So what was the discussion about Fourier transform? So in Fourier transform, we have represented the signal in terms of linear combination of periodic complex exponential. And basically that complex exponential was said to be the eigen function of that LTI system. So in this manner, like in Fourier transform, we basically represent the signal in terms of complex exponential. We have seen in the formulas as well. So that is a specific kind of representation, and we have shown that exponential signal as e raised to the power st, where s was represented as j omega. So here s is having only imaginary value, so we can say that s is your purely imaginary when we are discussing the case of the Fourier transform. So can it be generalized? So can s take some real value as well? So the answer is yes, because s is a very general kind of variable. So in a generalized manner, so if we consider the generalized form of s, in which it will take some values which is represented by sigma plus j omega, where your sigma represents the real part and this part represented the imaginary, then that generalized representation is called the Laplace transform. So this is the basic definition for the Fourier transform. So it is the generalized version of Fourier transform. So the next question arises that we have already have the representation of a signal in terms of Fourier transform. I have seen that that is very useful in getting the information about any type of signal and systems also, especially LTI systems. So why we need a different kind of transform as well? Like we have already seen Fourier transforms. So why Laplace transform is required? So the answer is that Laplace transform provide insights about signal and systems. So first it will do the work of Fourier transform. So it will provide insights about signals and various systems, and those can be analyzed by Fourier transform as well. So that can be analyzed by Fourier transform. So it is doing the part of Fourier transform, but in addition what it will do, they can also be applied to some very important context. So they can be applied some very important contexts, and these contexts are, for example, the Laplace transform can be applied to an unstable system as well. So that for an unstable system we cannot calculate the Fourier transform because the convergence doesn't happen. So for Laplace transform, this can be applied to some unstable system as well. So if we can analyze an unstable system, so they can provide some important role in understanding the stability of the system. So indirectly we can have an idea of stability of the system which was not quite evident with the Fourier transform. So in this manner, like Laplace transform is providing some additional information about the signal and system, which was not quite addressable by Fourier transform. So these are the advantages, and this is why we require Laplace transform in few cases, and we will get the idea as we move on in the lecture. So now we will try to have some mathematical representation of Laplace transform as well. So suppose response of a LTI system with ht as the impulse response, and the input is e raised to the power st, can be represented as, so this we have already discussed, so I am just giving it for the reference. So the output will be h of s e raised to the power st. You can refer to the lecture of eigenvalue eigenfunction, in which we have discussed like how this output is coming, and there we have said that this variable is represented as eigenfunction and this factor is represented at eigenvalue. So if we apply input as any complex exponential of the form e raised to the power st, the output will be the same input multiplied with some constant, and that hs value is represented as, so hs is represented as minus infinity to infinity h of t e raised to the power minus st dt. So this we have already discussed, and for Fourier transform case, what was the value for s? S was s of j omega. So this was happening for Fourier transform. And for any general value of s, which was sigma plus j omega, it can be referred to as the Laplace transform. So now for any general signal, how we can represent the x of s, that is the Laplace transform, that can be represented as minus infinity to infinity x of t e raised to the power minus st dt, and here sigma is, sorry, s is having a value of sigma plus j omega. So this is the definition for Laplace transform, and if we replace s with j omega, what will we get? We will get the x of j omega, so this is your omega, minus infinity to infinity x of t e raised to the power minus j omega t dt. So this is the representation of Fourier transform, and this is the representation for Laplace transform. So this is the difference, like here s is having real part and imaginary part, and here s is having only a imaginary part, so it is purely imaginary. So this is the understanding of Laplace transform. We can have an alternative understanding of Laplace transform as well. So here we try to see Laplace transform with a version of Fourier transform. So suppose we have seen that we have the formula for Fourier transform as x of j omega, which will be equal to summation minus infinity to infinity x of t e raised to the power minus sigma plus j omega t dt. So this is the definition for Fourier transform. So now what we will do, we will calculate the Fourier transform of sigma plus j omega. So what it will be? It will be basic. So I have done a mistake here. So this will be your j omega, and now that factor will be minus infinity to infinity x of t e raised to the power minus sigma plus j omega t dt. So here we have just replaced j omega with sigma plus j omega, and this is the Fourier transform. Now suppose we expand this factor of e raised to the power minus sigma plus j omega, what we will get? We will get xt e raised to the power minus sigma t multiplied with e raised to the power minus j omega t dt. So can you see that if we will combine these factor in one form and represent it with some variable, suppose b, so b of t, and it will be e raised to the power minus j omega t dt, that is minus infinity to infinity. So x of sigma plus j omega is basically Fourier transform of this factor b raised to the power t, and that is eventually xt into e raised to the power minus sigma t. So we can say that the Laplace transform is basically what? It is a Fourier transform of the signal xt multiplied with some exponential factor of e raised to the power minus sigma t. So this is the alternative way to understand the Laplace transform. Now we'll see some example to understand the Laplace transform in a better form. So for the example case, we will take a value of xt which is equals to e raised to the power minus at ut, and we try to calculate the Fourier transform of this signal. And here, for suppose we start with our Fourier transform representation, which we have already discussed. Here a is greater than 0 for the convergence of the Fourier transform. So x of j omega will be minus infinity to infinity e raised to the power minus at ut e raised to the power minus j omega t dt. And because of this ut factor, the limit will change 0 to infinity e raised to the power minus at multiplied with e raised to the power minus j omega t dt. And the output we have already discussed. Just for brevity, I am showing here the full derivation. So it will 1 over j omega plus a, and here a is greater than 0. So the Fourier transform for this signal is given by this expression. Now we'll calculate the Laplace transform. So the Laplace transform will be, we have seen the formula, we have x of s which is having the form minus infinity to infinity e raised to the power minus at ut e raised to the power minus st dt, and we will write it as 0 to infinity because of this ut factor e raised to the power minus s plus a t dt, that will be equal to 1 over s plus a. And as we have said that s is having a value of sigma plus j omega, so if s is replaced with sigma plus j omega, what will be this integral? This integral will be represented as 0 to infinity e raised to the power minus sigma plus j omega plus a t dt, and that will be equal to 1 over sigma plus a plus j omega. And from, if we compare this factor and this factor, we can say that this is the Fourier transform of this factor. So we have to just replace e raised to the power minus sigma t multiplied with our function. So this is the alternate representation. So we are calculating the Fourier transform of xt e raised to the power minus sigma t. And for convergence, what will be sigma plus a? That should be greater than 0. Sigma plus a can be represented in different form as real part of s should be greater than minus a, that is sigma is greater than minus a. So now what will be our final representation of the Fourier transform? So x of s should be equal to 1 over s plus a, and with the convergence will be real part of s should be greater than minus a. So this is the representation of the Fourier transform. Now we'll take a different signal which is represented with x of t which is equal to minus e raised to the power minus at u of minus t. So now we'll do the same mathematics to calculate the Fourier transform. So that will be minus infinity to infinity minus of e raised to the power minus at e raised to the power minus st u of minus t dt. That will be equal to minus of minus infinity to 0 because of this u of minus t factor. It will be e raised to the power minus s plus a t dt. And what will be xs? X of s will be equal to 1 over s plus a. The main part in this calculation is the convergence. So the real part of s plus a should be less than 0 because of this u minus t factor. So the convergence of this factor will be only possible for real part of s plus a which should be less than 0. So the real part of s, that is sigma eventually, should be less than minus a for. So what is the final output? The Fourier transform, the Laplace transform of e raised to the power minus at u of minus t should be equal to 1 over s plus a, with real part of s should be less than minus a. So as you can check that the Fourier transform value for both of this signal, so first signal was xt is equals to e raised to the power minus at ut, is having a form of 1 over s plus a, and again this signal which is different, that is minus e raised to the power minus at u of minus t, is having the same expression for the Fourier transform. The difference is in the convergence value of real part of s. So in real part of s, for the first case should be greater than minus a, and for this it should be less than minus a. So to understand this expression, we can have some graphical representation for the convergence value of s, and these values are called the region of convergence. So these are called the region of convergence, or in abbreviation we call it ROC. So these are the ROC basically depicts the set of value of s for which Laplace transform is defined. So set of values of s for which LT is defined, that is basically referred to as the region of convergence, and we can have a graphical representation to understand. So for the first case, so we have, this is the imaginary axis, this is your real axis, and this plane is referred to as S plane. So we have said that, and suppose this is the line for minus a, and for the first case what we have said, we said the real part of s should be greater than minus a. So for the first case, the region of convergence will be this plane, which is represented by shaded region, and for the second case, the real part of s should be less than minus a. So the shaded region will be this region. So these are the region of convergence for the respective example which we have solved. So now we'll see one more example. So suppose we have xt, which is represented as 3 e raised to the power minus 2t u of t minus 2 e raised to the power minus t u of t. So now we'll calculate the x of s, that is the Laplace transform, which will be equal to minus infinity to infinity 3 e raised to the power minus 2t ut minus 2 e raised to the power minus t ut multiplied with e raised to the power minus st dt. So we have just used the definition for the Laplace transform. So now we'll split this integration in two parts. So we will have our first function as e raised to the power minus 2t ut e raised to the power minus st dt. The other part will be minus 2 integration minus infinity to infinity e raised to the power minus t e raised to the power minus st u of t dt. So this can be represented as 3. Again it will be 0 to infinity because of this ut factor, e raised to the power minus 2 plus s t dt, and the other form will be minus 2 integration 0 to infinity e raised to the power minus 1 plus st dt. So what will be the final outcome? So the integration will be solved as 3 over s plus 2 minus 2 over s plus 1. So this is the expression for the Laplace transform. Now we'll see the convergence values. So for the first case, the expression was e raised to the power minus t ut, and its Laplace was coming as 1 over s plus 1. So we are discussing about this factor. So its region of convergence will be real part of s should be greater than minus 1, because we will put s plus 1 is greater than 0. So for the second case, it will be e raised to the power minus 2t u of t, that will be having a Fourier transform of 1 over s plus 2, and for this case real part of S will have a convergence for values greater than -2. So, and the final expression is basically the summation of these two values. So, we need some common region of convergence. So, let us plot the region of convergence for the both cases to understand the common region of convergence. So, we have one value as -1. So, this is the real part, this is the imaginary axis, this is your S plane, and this value is represented as -2. So, for the first case, what will be the region of convergence? It will be real part of S greater than -1. So, this is the valid values of S for which the Fourier transform e raised to the power -t ut is defined. And for the second case, what will be the region of convergence? It is real part of S greater than -2. So, this whole value will be valid. So, what will be the common area? Common area will be this. So, the value is greater than -1. So, the value is greater than -1 will be the common region of convergence. So, what will be the final expression? So, x of S for the given function will be represented as 3s over S plus 2 minus 2 over S plus 1, and the region of convergence for this expression will be real part of S should be greater than -1. So, in this form we can have the understanding of Laplace transform in this lecture, and we have solved some examples to understand it better. Thank you.